Okay, so good evening or afternoon, whatever time you watch this video. So the last time we were looking at, hopefully you don't hear noise at the background. If there is, poleni sana. Yeah, anyway, obviously you expect, let's see if I can make it bigger. Wait, how do you make it? Control L, full screen. There it is. Full screen. All right. Yeah. So yeah. I think the other time we introduced complex numbers. I mean, in fact, the slides are still continuation of this. And we talked about representation of complex numbers as in algebraic form, which is this one, z equals x plus iy. We say that the real part of this z complex number is x and the imaginary part is y. So for instance, if I give you z equals something like this, like what? Like z equals minus 2 minus 3i, then the real part of this complex number is minus 2. The imaginary part is minus 3, not minus 3i. Please note, okay? Anyway, now the next lecture, oh, I don't know why it's refusing to go back and forth. What has happened? Does it want me to? Okay, there it has agreed. Anyway, yeah, so this is the next one now. And what we want to talk about? I will talk about what we call a polar and rectangular form. In one moment, let me just close that door here. We'll close that door outside. Yeah, close this one. Okay. Okay, so yeah, so polar form, rectangular form. So as you can guess from the representation of a complex number z in the form of x plus iy, the x part can be considered as like x units on the x-axis, and the y, the imaginary part, y, that can be the y-axis. And so I don't know what the next slide says, but basically you can describe a complex number in two ways. One, it can be in this form where you have if this is, let's say a complex number, let's say call it Z, all right, in the complex plane. So this is your Z here. And so Z can be described this way, X words, Y words, which we used to write in geometric form as, you write X axis value and the y-axis value. You remember that we did that last time, eh? Which, of course, now in algebraic form, you can just say z equals x plus iy, all right? So really, as you can see, this is more like a rectangular form, if you want me to say, because this is the rectangle kind of form of the coordinates, all right? So that's one way of describing a complex number in terms of x and y values. That would now correspond to the rectangular form. You can see a rectangle there. Or you can describe this z. Actually, ideally, our z, this point, this is our point z. Okay, so this should not be there. This I can remove this so I don't want to mislead you, all right? Especially this is recorded, so if it goes down to history that I lied to you and it's on record, that's not good news, all right? So our z equals x plus iy, or x comma y, the geometric form, remember? So that's one way of describing it, and this is what we call a rectangular form. And then you can also describe this z, I mean, this we're assuming this is more like the origin, all right, in the x and y axis. The x-axis, real axis, imaginary axis. Actually, here in complex analysis, we talk of the real axis, the horizontal one. This is x-axis. And then we call the imaginary axis the y-axis, okay? Or we can describe this in terms of this length, r, array, some length r, and then measuring from the horizontal axis, the x-axis, an angle theta, all right? So we would say that z is also z, can also be said to be, I can put it in geometric and algebraic form. In geometric form, I would just say it is r, comma, theta. So when I write this at the back of your mind or my mind or our minds, ideally, we should think of this r or ray or length And then you measure this angle. Of course, this ray can be here, can be there, and so on like that. And so now we have this polar form is this. Of course, here I'm not written or this is the same as z equals x plus iy. All right. So this is very important as we build. This is x plus iy. Remember what we're calling the rectangular coordinate form. Remember. And so now having this, we can move to this. You see, I mean, if you have x and y values, you can describe it also in terms of the r theta form. There's a relationship. And so here you can see that if you take the cosine of this angle theta, cos theta is basically this adjacent. Remember, this is a right angle triangle, okay? So the adjacent there is x over the hypotenuse, which is r, all right? And so x equals r cosine theta, because cosine theta is x over r. Likewise, y, we look at the sine of this angle, is y over r, the opposite over the hypotenuse. So that means sine theta equals y over r. So y is r sine theta. That's what you have. And now the relationship between r, y, and x is that r, by the Pythagoras theorem, is x squared plus y squared square root, which is that. And then also this angle, the tangent of this angle is y over x. All right. So theta is the tan theta of this, or arctan of theta. All right. All right. Next, I hope this thing will agree. It tends to misbehave. All right. How do I do that now? Sorry, let me close this. They want me to move to the next slide. Okay. Now, having done that, I hope this will not mess you up. I think we can remove this. So allow me to remove it. So you can see. So far, so good, I hope. Well, it has to be. So next, let's see how much time. Just 7 minutes gone. Right. So what do we have? So now, polar form and argument. So we've defined now the polar form and the rectangular form of a complex number. All right. So for any complex number z, this one is, we have the polar form, which is z equals, well, something I didn't say previous slide. I don't know whether it will agree for me to go, but I can just write. You see, we say that z is what? Is x plus I y, all right? But then x is r cosine theta and y is r sine theta. So in polar form, now you translate from z equals this. You can move from the rectangular form to this form because x is r cosine theta and y is r sine theta. So you can express now z from the rectangular coordinate form to the polar form in this way. So you'll have that z is r sine theta plus r cos theta plus I sine theta. And now there's something here we call the Euler function. And one moment here, that people disturbing me. Wait, close this door. Close that door. Don't make noise. Okay, so well, this expression here, so this part, all right, cosine theta plus I sine theta can be expressed as exponential I theta. This is the same thing. E, the exponent E, remember E, the complex number E, not complex. The rational number E, which is 2.718 something, power I theta, all right? What I've written exponential I theta is the same as E I theta, all right? And this one, we call it the Euler, is it Euler function? Yeah, it's the Euler function, okay? And so here we have a definition, polar form and argument of Z. So Z, which is x plus Iy equals, the x is r cosine theta, the y is r sine theta, which is this, and this can be translated to r ei theta, all right? And now here's something else I have not told you, which I can tell you from previously, is actually theta is periodic. You know what it means that an angle is periodic? What it means to be periodic is something like, if I give you an angle 45 degrees, all right, which by the way, okay, 45 degrees, so maybe I can say 180 degrees. It's good to get used to this, either degrees or radians. So 180 degrees is the same as pi, yeah? Okay, pi radians, okay. So 45 degrees is pi over 4 radians. Just for you to get used to this kind of units. So 180 degrees is the same as minus 180 degrees. Now, what do I mean by that? Now, let's see whether it will allow me to go back. One moment, please. Does it allow me to go back? You know, it keeps misbehaving. I don't know. Anyway, fine. I will not go back so I don't mess it up. So, you see, when you're thinking of measuring angles, how do you measure angles? From this way, if you go that direction, this is a positive. Like if I measure 45 degrees, is that way. Okay? So, if I go around 360 plus 45, I get, what is 360 plus 45? Is 405, right? 405 degrees. So 405 degrees is the same as 45 degrees. Or if you don't like that, you can go to 180 degrees. 180 degrees. If I go this way, I measure 180 degrees positive direction. If I go the opposite direction, I go to the same place, it's minus 180 degrees. Or the easiest is 0 degrees. 0 degrees is the horizontal one. If you go around and come back, that's 360 degrees. So 0 degrees is same as 360 degrees, is same as minus 360 degrees, is same as 1, 2, 720 degrees, or minus 360, minus 360, minus 720 degrees. Now, this is what this says, that angles are periodic. So any angle will always be theta is the same as theta plus 2 pi k. 2 pi k is just the periodicity. Like when k is 0, it's just the angle. When k is 1, then you are rotating pi degrees. Like the way I was saying, 0 degrees, you can go 360, goes back to the same place. Or minus 360, so it's k is 1 or minus 1. So the angle theta is called the argument of the complex number z. The argument of z is theta. And if theta lies between minus pi and pi, theta is called the principal argument. Now, where is minus pi to pi? Well, minus pi is this direction, and pi is that direction. All right. So, I mean, if you think of it, I don't know whether, I'm sure this makes sense to you. This is what is basically minus 180 degrees to 180 degrees. We're talking about principal argument. Okay. For instance, if you take, you see, since the angles are periodic, you will take the angle when you represent in this form that lies between minus pi and pi. Okay. For instance, if I'm talking about 45 degrees, 45 degrees, we have said is the same as 405 because it's just 45 degrees plus 360 is 405 or minus 360, which will give you minus 315 degrees or something like that, right? So 45 degrees is the same as, I mean, you can write it down if you like. So you will have 45. I can write it here for you. I mean, this lecture is pretty, you know, we enjoy ourselves. So I can say 45 degrees, we've said is the same as, if you add 360, now I'm representing in degrees form. Plus 360 is 360, I get 405. Is that right? I hope I'm not lying to you. That would be terrible. And it's recorded again, we've said. It's 405 degrees. If you take 360 minus 360 plus 45, which is the same as, I can say again, minus 315 degrees. Okay? In terms of periodicity, these three angles are the same. So which one would be the principal argument for a complex number? The principal argument would be the one that lies between minus 180 and 180. You can see 45 degrees lies between, I mean, it's there, minus 180 and 180. How about 405? 405 is way outside. I mean, it's way greater than 180. Minus 315 is also way outside. So really, the argument for whatever complex number you have that will give you these three angles would be, now, one moment, my kids are making this. Wait, guys, close the door here. Wait, close this door and stop making noise. Sorry, guys, the video will have entertainment. Anyway, commercial break, why not? All right, so, yeah, I mean, that's it for the definition. So I give you an example. Example number 1. Express this complex number in polar form. So what you are given here is X is this is X, and this is Y. X is 1, and Y is minus the square root of 3. So here it is actually. So, and then what's R? We said R is the square root of X squared plus Y squared, added. So X squared is 1, and then Y squared is 3. When you add, you get 4. The square root is 2. So R is 2. So in other words, I've given you the X and Y values of Z. So give me the R and theta values of this guy. That's the polar form. So now here we look at it. We have and theta. What did you say theta is? We say tan theta. If you remember, now here again, I will maybe repeat things that you already know, but anyway, fine. Tan theta, we said is Y over X, all right? Divided by X. So what is Y? Y is minus root 3, and X is 1. So theta is minus root 3, rather, tan theta is minus root 3. So how do you find theta? You find the tan inverse of that, okay? And now here, I will teach you some way of trying to identify this. The moment you are given X and Y, you can try to sketch and see exactly where it lies so you can tell, the angles. So really, in this case, I sketch for you here. I mean, very fast. We have, this is our X, and this is our Y. So the Y value X is 1, so 1 is somewhere here, all right? And what is Y? Is minus the square root of 3. So where would that be? It would be somewhere under here. The square root of 3 is how many? It's about 1.7 something, right? Yeah, because, yeah, it is 2.89 something. So it's somewhere here. So really, this is what we are talking about. So our complex number is that one. This is our Z that we're given, all right? So the angle you're looking for, ladies and gentlemen, is this one here, okay? And that angle, you can actually say is that you're measuring angles negative words, but you can do something here like a mirror to make your life easy. If you measure, I mean, if you take this is, I can say this is minus the square root of 3. And so if I take the square root of 3 up here, so this is now the other side. So this angle, theta, is same as that angle, size-wise, but then this will be negative, this angle, okay? So what would that angle be? Of course, you can compute in your calculator if you want. So this is, what is this? Now I'm supposed to give you a quick solution to think about. So this is, remember, sine and cosine. Now here, I'll teach you some tricks here. Sine over cosine is what gives you tan, if you remember. So the question is, which angle whose sine is the square root of 3 and cosine is 1? All right. And if you remember, we are talking about 1, but there's something else that here I'm not telling you. You know what I'm not telling you? About R. What's this length? This length here is 2. Right? So now if you punch in your calculator, all right, you will find, I mean, so basically what I'm asking you is, we are talking about the square root of 3 over 1, or the square root of 3 over 2, 1 over 2. Now this would tell you the angle. So really what I'm translating, I'm trying to work out this without a calculator. I mean, if you punch in your calculator, you get your answer. But if I don't know, what do? I'm just saying which angle tan of theta is, now I'm working out this one, then I'll just negate the answer. So I'm working out, so I'm talking about the square root of 3 over 1. But in terms of angles, this never happens. You have an angle, you have sine and cosine. There is no moment where you will have an angle has a cosine which is 1 and there is a non-zero sign. Because remember, the cos of 0 is 1. The sign of 0 is 0. So that doesn't work. So what you do, you modify this. This is the same as saying, which angle, sine theta over cos theta, is the same as the square root of 3 now. I have a 2 somewhere here. You can see this 2. So I just divide by 2. It divide by 1 also. Divide by 2. This is the same as this because I've just divided by 2 divided by 2. So now which angle has a cosine of a half and a sine of root 3 over 2? And that angle, if you check, I don't know whether in your earlier life you learned about the 30, 60, and 45 degrees. Those are special kind of angles because the cosine of 45 and sine of 45 are the same. They are 1 over root 2. The sine of 30 is usually a half. The cosine of 60 is usually a half. So it turns out that that angle is 60 degrees. 60 degrees, this is 60 degrees. If you check, you find cosine of, your calculator, just take the tan inverse of the square root of 3, you will end up with 60 degrees. Okay, this will be 60. Okay. And this, if you translate in terms of radians, is just divided by 180, it is pi over 3. So really, this angle is pi over 3, but the one we're looking for is the negative one. So this turns out to be minus pi over 3. Okay? So the argument here is minus pi over 3. And so the answer, this one in polar form is z equals r cosine theta, which is cos of minus pi over 3, plus I sine minus pi over 3. And that's it, ladies and gentlemen. I hope I've not taken too long on this. Next, we go to now some propositions here. Oh gosh, now my screen is dirty, so we need to clean it. So let's do that very quickly. And I'll give you a commercial break of sorts. Now there will be noise, but it's fine. Now the next few minutes, I want to run through the lecture very fast. Anyway, the notes are pretty straightforward somehow, but I'm more or less clarifying things. So operations on polar form. So polar form means that R1 cosine theta 1 plus I sine theta 1. So given two complex numbers, Z1 equals R1 cos theta 1 plus I sine theta 1, and the next complex number, Z2, is R2 cosine theta 2 plus I sine theta 2, then we can multiply, we can add, we can divide, we can find modulus. Okay, so the product of these two guys, you can multiply out, and it turns out that Z1 times Z2 will be, this is R EI theta, all right, times R1 EI theta times R EI theta 2. So it ends out being R1 times R2 EI theta 1 plus theta 2, which is this. You can expand that to check that. And then when you divide, you have this kind of thing. So EI theta, this goes up, it becomes R1 over R2 EI theta minus theta 2, which is the same as that. Okay. So this you should be comfortable with this. If you are not, I will clarify for you, but that's that. Then proposition here. The modulus of two complex numbers, Z1 times Z2, is same as individual modulus is same as the modulus of the product of the two guys. And likewise, here we have something we shouldn't be having. What is this? This one here. So again, when you take individual moduli and you divide, the same as dividing first and taking modulus. Okay. And then lastly, you have this argument that the argument of the product of two complex numbers is the sum of the arguments of the two guys. And the argument of the quotient of the two guys is a difference. And this is just what this is saying. The argument of Z1 is theta 1. The argument of Z2 is theta 2. When you multiply the two guys, you end up with the argument is theta 1 plus theta 2. All right? And then when you divide, we end up with the argument is the difference of the two guys. That's fine. Good. All right. Next. Let's move next because I want to make sure the lectures are not too long. All right. So example number 2, determine, well, given Z1 equals I and Z2 equals 1 minus I root 3. So you perform all these three. You multiply, you divide, find the argument of the product, find the argument of the quotient. So if you multiply these two guys, Z1 times Z2, of course, you can do the multiplication pretty straightforward. Z1 times Z2 will just be I times 1 is I. Is it? Yes, it is. And then I times minus I root 3, it becomes root 3. So it's just root 3 plus I. I hope that's clear. And so now, and then, wait, so first we are doing them. We actually multiply. These guys are in rectangular form. We want to convert them into, well, we have to convert them into polar form, or we can just multiply and express them into polar form and read what we want. Read the argument of this and so on. So Z1 times Z2 is that's it, is finished. Division of the two guys, this we did last time. So Z1 over Z2 equals I divided by 1 minus I root 3. Remember how we perform this? We multiply by the complex conjugate of the denominator. So this becomes I divided by 1 minus I root 3 times the complex conjugate of this guy, which is 1 plus I root 3, divided by the same number. And so here, if you perform the multiplication, it turns out the numerator, we already said is root 3 plus I, is it? This guy multiplied by this, you get I, and then you get minus root 3. So it's minus root 3 plus I. The denominator, remember, I don't know you remember that when you multiply a complex number times its complex conjugate, you get a square of the first guy and the last guy, sum of the squares, okay? So it's just 1 squared plus root 3 squared. So it's 1 plus 3, which is 4. Are we done? Yes, we are. Next. For z equals I and z2 equals 1 minus root 3, well, we're still working out the complex now. So previously we were asked to find the product and the quotient. Now we are asked to find the argument of the product and the argument of the quotient. So here now there's some work to be done, which probably I should talk about anyway. So what do we have? So we found that the product of these two guys, when you multiply these two guys, oops, what do you get? Oh gosh, why is this guy misbehaving? Okay, I've seen you. Right, so Z1 times Z2, we say this gives you root 3 plus I. All right. So here, let me just look at the solutions that I put it. So this is Z1, I mean, the product. This times this is Z1 times Z2. All right. So now we want the argument of this guy. Which just means you need the polar form, the angle. All right. So how do you find that? Well, one way, like I did here, I think I said here from argument of Z1 is pi over 2. Now, how does that come about? The argument of Z2 is minus pi over 3. So, for this one, I can say we already worked out. The argument of Z2 is the one we did previously, if you remember, which was 1 minus I root 3, was minus pi over 3. The argument of Z1, I can explain to you why it's pi over 2. Now, what is this? So, this is 1I. So this is the x value is the real value. So I can say this is 1, if you want me to say. And then the I part is just maybe 1, 2. So this would correspond to the I part, if you want me to say. So really, this one, let me just highlight it. This is our Z. This is Z equals I. So what's that angle? The angle it makes with this axis is 90 degrees. You can look at it that way. You can see it, eh? Or, so that's why it's pi over 2. 90 degrees is pi over 2. 180 is pi. 90 degrees is a half of pi. So it's pi over 2. The argument of that is pi over 2. Or if you don't like that, you can just say x is 0 here. And y is 1. What am I talking about? The rectangular form of this number Z1 is 0 plus I, or 1I. So the real part is 0, and the imaginary part is 1. So theta, which angle theta or tan theta? Let me just write t theta. Okay, this tan theta equals y over x, but then y is 1 and x is 0. There's 1 over 0. So which angle basically the sine of an angle whose cosine is 0. We already said it, if you remember. The sine of 90 degrees is 1. The cosine of 90 degrees is 0. So that angle turns out to be pi over 2. You can punch in your calc. Of course, it won't give you the answer because it will get confused anyway. Because 1 over 0 is an infinite. So the argument of Z1 is pi over 2. The argument of minus pi over 3, of Z2 is minus pi over 3. So the argument of the two guys is just add. So pi over 2 plus minus pi over 3 is pi over 6. Or you can work out this one. Express this in polar form and see that it turns out that theta will be pi over 6. You work that out, okay? Again, if you have problems, I always tell you, you can ask me, you can reach me, you can always find me. All right, now the argument of the two, when you divide, the argument is a difference. So just pi over 2 minus pi over 2, which is 5 pi over 6. Again, you can work out what we just did previously and see whether you get that, okay? Fine. Now, the last part of this lecture, I didn't want it to make it long, but I guess you guys have time, you need to study, is what we call roots, powers of complex numbers. By the way, I hope you guys are reading, because if you don't read, you'll have issues. I hope power doesn't go away. If it does, we'll be in trouble in this video. Anyway, fine. So what is it I was going to tell you about? I was going to tell you about powers of C. So let me try to follow the slides so I don't feel freestyle, okay? So given Z, some complex number Z is X plus IY. This is the rectangular form and the polar form is REI theta. Then we can raise, I don't know, this to any, we can take any number. It can be an integer, it can be a real number, it can actually even be a complex number. We can raise this guy to power n. So let's start with integers. So Z power n will just be this number raised to power n. Here you would have to use binomial expansion if it's in this polar form, or you apply something else called the Moivre's theorem, which is what is here. So this you raise to power n is just r power n. So actually this should be here. Now this is a mistake. Can be correcting our notes here as we move on. Let me write with a pen, a different pen. Hopefully it's nice. So this is supposed to be, this is power n. Oh, no, this is too fast. Sorry. Okay. So this is power n. You see, Z power n will be this a raised to power n times this power n, which is e power I n theta. So r power n times cosine n theta plus I sin theta. So this is just saying what we have actually taken a shortcut of is, you see, Z is the same as r cosine theta plus I sine of theta. All right. So this is a polar form. So if we raise this to power n, this is also raised to power n, and this is raised to power n. So let me raise to power n, power n, power n. So here this corresponds to this one now. This part corresponds to this part. Meaning what? Cos theta plus I sin n sin theta raised to power n is same as this one. Cos theta plus I sin n theta power n is same as cos n theta plus I sin n theta. That makes our life pretty easy. And so, yeah. So let's look at an example here. So the example says compute z cubed, given that z is 1 minus I root 3. This we already did in polar form. It was z equals 2 cosine minus pi over 3 plus I sine minus pi over 3. So when we raise to power 3, then the r is just 2 cubed. Then cos minus pi over 3, this you just multiply by 3. It becomes cos minus pi plus I sine minus pi. And just for the sake of the record, if you punch in your calculator again, I don't know that you would want to do that. But it turns out that this one equals, is it 1 or minus 1? Minus 1. And this one here is 0. So 8 times minus 1 is minus 8 pi. If you punch in cos minus 180, it give you minus 1. Sin minus 180 is 0. And that's why you have that. Okay, fine. Fine. Okay, let's move next. The next one now, this one is pretty interesting, pretty, I don't know, can be complicated. Perhaps it depends on how you look at it. So let's look at it. Let me see how much time we have. I think we can make it 5 minutes and then the lecture should be over. And then you'll have just to replay it. And if you have need examples, I'll give you, of course. So what we have looked at previously is powers of complex numbers. You raise complex numbers to integral powers, integers, okay? I don't know, z cubed, z power 4, and so on like that, okay? So in summary, if you're given a complex number in algebraic form, that's x plus iy, if you raise it to power 5, you know the binomial expansion, that would be pretty tedious. So what do? Express it in polar form, use the Euler identity, REI theta, you have theta, raised to that power, and then you just punch in using the Moivre's expression. You know that one, of course, theta plus I sin theta, power n, the same as cos n theta plus I sin n theta. That's something we just looked at before. So if you don't get it, go back, okay? So the next thing is now, once you can talk about roots, now you can take, you can, in mathematics, we sort of have, we apply a forward push and a backward push. So integrate, differentiate. So raise to power or unraised to power, that's called taking roots, okay? So like, if I give you a complex number Z, I could ask you to find the Z raised to power 1 over n. That's the nth root of Z, all right? That's basically what we're looking at here. So a complex number W is the nth root of Z. So this is just saying that this is same as saying W is the nth root. Is this one here. If W power n is Z, or W is Z raised to power 1 over n, this is the nth root. In fact, just saying that, yeah, I can write like this. Nth root of Z. This is equivalent to saying what? That Z equals Z raised, W equals Z raised to power 1 over n. So can we always find this? So if W is, well, remember any complex number can have a polar form or a rectangular form. So if I have a complex number W and I want to call Z, so both have their polar form. So W's polar form is R cos phi plus I sin phi. And the polar form of Z is R cosine theta plus I sin theta. Then we can now apply this thing. And what happens? That Z, this complex number W raised to power n is Z. So this now you translate is that this guy raised to power n, rho power n, cos n phi plus I sin n phi. That means if you raise this to power n, you get Z. So that means this guy corresponds to this guy. So of course now you'll have this correspondence. The correspondence is there and there. So that means rho power n is R. All right. This guy corresponds to that guy. So that means rho is the nth root of R. And then the angle cosine n phi corresponds to cos theta. So that just means, and sin n phi is sin theta. So that means phi is, what is phi? It's just, well, of course, obviously phi is, phi is theta over n, right? But angles are periodic. Well, that just meant theta is the same as theta plus, let's write a proper one, 2 pi k, where k is an integer. So basically, it turns out that phi is theta plus 2 pi k over n. All right. And thus, the nth roots of Z, which is given that polar form, will be given by WK W sub k equals, you raise r to power 1 over n, the nth root of r, times cosine of theta plus 2 pi k over n plus I sine theta plus 2 pi k over n. And then you just vary k. Then you get the roots. Okay? Depending on what k is, k can be 0, 1, 2, 3, and so like that. Okay? That's the way you compute the complex roots of a complex number. So let's look at an example. And then I think we'll be good to, gosh, this lecture is going to be very long. So, remark, geometrically, the nth roots of a complex number are n of them, and they span a regular n-gon. Regular n-gon means that if there are 3 of them, if you're finding the cube root, if the n was 3, you're talking about cube root, then there will be 3 roots, and the 3 roots will span an equilateral triangle. If there are 4 roots, there will be, no, if it's 4th root, or if it's square root of z, then there will be 2 roots. And the 2 roots span what you call a line, because they'll just be like this. If there are 4 roots, it's 4th roots, there will be 4, and they form a square, and so forth, and so on. Okay, so let's look at an example. I'm hoping this is the last slide, so I don't want to make this lecture pretty long. It's really, really long. So find the 3 cube roots of z equals I. Let me just remove this one. So hopefully this is okay for you. Let's just erase so that our slides can be, clean as we move on. So example. So find the 3 cube roots of the 3 cube roots of z equals I. Okay. So you know what that means you need to do? The first thing you need to express this in polar form. Because you need an angle, you need theta, you need r. And then you use that formula we had, okay? That is wk equals r, nth root of r, in this case is cube root of r, cosine theta plus 2 pi k over n. In this case, n is 3. So, in this case, we already say the argument, when z is I, the argument of the angle here is just pi over 2, all right? And r is 1. Why? Because x is 0, y is 1. So 0 squared plus 1 squared square root is 1. So r is 1. So the 3 cube roots are given by, so 1 raised to power, well, the cube root of 1 is 1 times 1 times 1, cube root is just 1, all right? And then now we have wk will be cos pi over 2 plus 2 pi k over 3 plus I sine pi over 2 plus 2 pi k over 3. Now our k should be 3 numbers, okay? Because we are looking at 3 cube roots. So they can be 0, 1, 2, or 1, 2, 3, or minus 1, I don't know, 0, 1, and so on like that. Remember, k is an integer, okay? Why is k an integer? Because we said k is the idea of periodicity. Periodicity means you start from 0, you go to 1, 2, 3, or you go minus 1, minus 2, and so on like that. So when k is 0, we have w0 will just be cosine. This is 0, so it's just pi over 2 over 3, which is cosine pi over 6 plus I sine pi over 6. And that's it. This corresponds to the principal third root. Why principal? Because it corresponds to pi over 6, which is 180 divided by 6 is 30. So 30 degrees lies between minus 180 or 180. And then the other roots, wk, k is 1. You just put 1 here. You have pi over 2 plus 2 pi over 3. This is how many? 4 plus 1, 5. So you have 5 pi over 6 plus I sine 5 pi over 6. And lastly, when k is 2, you just have cosine pi over 2 plus, this is 2 times, I don't know, 2, so it's 4 times 2 is 6, 7. Is that something like that, or I'm wrong here? Eh? So k is 1, 2. So in k is 2, this is 4, 5, 6. Anyway, I don't know. I hope I didn't make mistakes. Eh? So this is W2 is cos 3 pi over 2. Why is 3 pi over 2? Let me just check this one here. When k is 2, here you have 4 pi. So you have pi over 2 plus 4 pi over 3. So this you multiply by 2, it gives you 8. So 9. So it's 9 pi over 2 over 3. Yeah, it's 3 pi over 2. It's okay. Yeah, no problem. So this one, when k is 2, this will be 2. So 4 pi over 2. We put them as a decimal, the LCM, it will be 8 pi plus 1 is 9 pi. So it's 9 pi over 2 over 3. So the 3 divides the 9 becomes 3 pi over 2. And so, ladies and gentlemen, these are the three roots. This and this. These are the three roots of the 3 cube roots of z equals 1. I don't know whether there's any other. Maybe this is the last, I hope. So the last example is, I think you go through this and that's it. Okay, let me just say, find the fourth root of z equals 1 plus I. So again, x is 1, y is 1, radius r is the square root of 2. So the argument is tan inverse of 1 over 1, which is pi over 4, 45 degrees, okay? And so the fourth root, now you go to the formula. WK is the fourth root of r, which is root 2, cosine pi over 4 plus 2 pi k over 4 plus I sine pi over 4 plus 2 pi k over 4. K will be 4 numbers, either 1, 2, 3, 4, or 0, 1, 2, 3, and so on. So just punch in these values in here and get the values, and then you are done. Ladies and gentlemen, that's it. So you have one more example, which I think it's been solved for you. This you can check. I wanted to finish there. So that ends my lecture. I hope you guys will be okay.